Projective transformation. This video of mine is a projection of the real world onto the photographic screen or the CCD of the camera. It projects the three-dimensional world in a two-dimensional plane. This projection is affected by the optics of the camera, and this projection is called a perspective projection. Apart from perspective projection, you have orthonormal projections, which is used for drawings of buildings, mechanical structures, where the aspect ratios have to be maintained so that the drawings and or mechanical structures can be constructed. Let us see these projections. Projection transformation, orthonormal and perspective. Let us first take the taxonomy of projection. Projection is a representation of the three-dimensional world in a planar geometric, in a plane. So the planar geometric projection is divided into two parts. One is parallel projection and the other is perspective projection. So let us first deal with parallel projections. Parallel projections can be seen as orthographic projections and oblique projections. Orthographic projections are generally done for designs, like if I would like to have a building made, I would make a blueprint of the top plane, the front elevation, the side elevation, and I could also make an axonometric, that is isometric, and other projections. The other type of projection, apart from orthographic projection, is oblique projection, where I would take a projection in an angular manner, where I can have a projection which is cabinet, cavalier, or any other angle of projections. On the other side, perspective projections, we will deal with 1 point, 2 point, and 3 point perspective projections. We will also see how these projections can be represented in a form that we could use with other transformations, that is, as a 4x4 matrix transformation. Parallel projections. Center of projection is infinity. Direction of projection, same for all points. That is, you make a straight replica of every point onto a plane. So if I have the plane as shown here, the viewing plane, I could draw perpendicular lines from the 3D objects. Wherever it intersects with the plane is the point which is shown as a projected image. So orthographic projections perpendicular to the viewing plane. So I could have a front view, a top view, and a side view. I have this structure which is a Greek pantheon-like structure, and this Greek pantheon-like structure can be seen as a front view, top view, and side view. These views are helpful if I would like to construct this building, or it is used in civil engineering in the blueprint of buildings when the buildings are being constructed. The oblique projections, that is, not perpendicular to the view plane. we have a standard two oblique projection. One is called the cavalier and the other one is the cabinet. Cavalier is at an angle of 45 degrees, which amounts to a tan phi equals to 1. On the other hand, cabinet projection is for an angle of approximately 63.4 degrees, which amounts to a tan phi of equal to 2. So these are two standard methods of projections. One could choose any other angle to a choice and do a projections in of them. For orthographic projections, it is simple because what you have in an orthographic projection is that the z component is no more valid, or z component becomes 0, while the x and y remains the same. That is, x prime is equal to x, y prime is equal to y, while z prime will be equal to 0. This can easily be represented in a matrix form as shown here. This matrix looks like a unitary matrix except for the z component is made 0 here. The original world units are preserved, pixel units are preserved in this case. Now, orthographic screen space transformation. Supposing I have got a location where my screen is defining this corner as 0, 0, while the opposite corner is the maximum pixel in X and maximum pixel in Y. And this be mapped to a physical coordinate of the world as bottom equals to 10 meters, top equals to 20 meters, and left is equal to 10 meters, and right is equal to 20 meters. Now, this portion of my real world needs to be represented in my projected screen. And this can easily be done by representing this as a form. Here what you see is width divided by right minus left, height divided by bottom minus top, and z max divided by far minus near. These three quantities are basically the scaling quantities which scales the real domain into pixels of the type that we would like to observe in our screen. We could take the amount to be the same to have an isotropic scaling. Otherwise, the scaling can be anisotropic also. But since my origin is not the origin of my world, there has to be a translation. The translation is given here. Minus left multiplied by width divided by the normalizing term right minus left, minus top multiplied by height divided by bottom minus top, and minus near multiplied by z max divided by far minus near. This vector, what you see on the right hand side, is the translation term which is used to bring the corner of the box to the location of the world that we would like to observe. The left, right, top, bottom refers to the viewing frustum in the model coordinate. The width and height are in pixel units. This matrix scales and translates to accomplish the transition in units. Now let us go to the best projection is images. Images are projections of the real world into a two-dimensional screen. The camera projects the three-dimensional world. It focuses using lenses a three-dimensional world onto a CCD or a photographic plate which records the three-dimensional world as a two-dimension. But the projections recorded by the camera show an interesting feature. What you see is that the parallel lines seem to converge. In this case, it is the road and the trees. These are converging into a single point known as the vanishing point. The blue line shows the horizon on which the axis or the lines are vanishing. It's called the horizon. The other image has a similar effect. Here we again see that there is a single vanishing point and all the lines seems to be vanishing at a particular point which we denote as the horizon. In this case, again, the position of the camera has changed, but there is still a single vanishing point where this camera picture, all these parallel lines are converging to. You see a similar effect here. In this case, you have a road which is turning, and you see here that was a conversion to the vanishing point. Here again, this converges to a vanishing point. The position of the camera, the tilt of the camera is different. Again, here you see it's all vanishing to a single point on an imaginary horizon. Here again, these are views of the campus, and whatever picture that I take gives me a similar effect where parallel lines are converging to a singularity or a single vanishing point that is at the horizon. Now here what you see is that there seems to be two vanishing points. Due to the curvature of the road, a portion, the front portion of the road vanishes at a particular point, while the other part of the road vanishes to another point. But both these points are on the same line, which is the horizon. This is a two-point vanishing image where both the points are on the horizon. In this case, you see again that this is again two-point vanishing function, but in both the cases, the the sections of the road are vanishing on the horizon at two different points. Here again, we see a similar effect. Two sections of the road are vanishing on the horizon, which is denoted by the blue line. We see here that a front portion of the road vanishing at a particular point, and if I take the latter portion of the road, it is vanishing at another point. But both of them are on the horizon line denoted by the blue line. Here we see again vanishing at a single point. These are different locations or images of the IIITA campus, which shows you that parallel lines are converging towards a single vanishing point. Here again, we see there are two vanishing points because the road is curved, and because of the curvature, the road exhibits two vanishing points. Here we have a single vanishing point. Again, here we have a single vanishing point. Again, here we have a single vanishing point. You see the hedge, the height of the hedge being the same, vanishes at the same point, which is same to that of the road. Here again, we see similar effect. We also see the roofs of the building, which are parallel to the road, showing a similar effect of a vanishing point at the horizon. Here, assuming that the trees are of the same height and the building, we see that it vanishes in a single point. Again, here there is a vanishing. The building as well as the road are vanishing at a single point. Now, perspective transformation was first discovered by Donatello and Brunelleschi and Da Vinci during Renaissance. Objects closer to the viewer looks larger. Parallel lines appear to converge to a single point, as we see in this figure given here. In this figure, we see that there are two vanishing points. One of the very famous paintings by Da Vinci is the Last Supper of Christ. In this, Da Vinci has explored perspective projection, perspective projection. How many vanishing points can a perspective projection have? In this building, if we connect the edges non-horizontal to us, we see that they all converge to a single point. So when we see a building face front, it normally shows a one-point perspective. When we observe the same building from an edge or from a corner, it describes a two-point perspective, as you see here, but as you see here, both the edges converge on to a same plane or same line, which is the horizon line. This is a 2-point perspective. Now, if I see this building from an angle so that I have a third dimension also placed, then I could, like here as shown here, I will then have a 1-point projection or 1-point perspective projection, a 2-point perspective projection, and a 3-point perspective projection. Since the world is of 3 dimension, the maximum number of vanishing points that a perspective projection can have is 3. But due to looking at the image from specific angles, these vanishing points may superimpose on each other, and therefore a 3-point vanishing can reduce to a 2-point vanishing or to a single point vanishing. So in this case, this is a 3-point perspective image where I have 3 vanishing points. So here we have on the right hand side a 1-point perspective, 1 vanishing point, 2 points perspective, 2 vanishing points, and 3-point perspective, a 3-point vanishing point.
In this video, we're going to quickly go over how to do 1 and 2-point perspectives. There's a couple things they have in common and a couple of differences that they have. I want to make sure we're clear on all of them. So take a look at 1-point perspectives to start off with here. The first step always is to start with a horizontal line. That horizontal line that you start with is called a horizon, and that happens for 1 and 2-point perspectives. But just for this one, make sure you're happening with 1-point perspectives. Once you have that, you're going to draw a single point on that horizon. That point is called the vanishing point. Once you have that accomplished, you're going to draw your front view. So if I'm drawing this cube, which I'll do in just a minute, I want to draw the front view, which is going to just be a square here. We'll add on our right and top views in just a moment. Once you have that drawn on there, you want to draw construction lines back to your point, and we'll make that a little bit more clear here in just a moment. And then finally, add your right and top views. So let's go through an actual working of this and see how it functions. So the first thing I'm going to do is I'm going to go in there and I'm going to draw in my horizon point. Once I have my horizon drawn, I'm going to add a point. It can be anywhere on that line, doesn't matter, just needs to be on that line. And generally what you want to do is you want to draw your front view to the left or to the right of that point. Since I drew my point on the right, I'm going to draw my square down here on the left. So I'm going to start off with my front view, and that's roughly my front view. If you're going through and actually drawing it, you'd measure it out and make sure it's correct. But in this case, that's what I'm going to go with for right now. Then I'm going to take construction lines from any of the corners back. So I have 4 corners. I'm going to draw my construction lines back to that single point. The only one I'm not really concerned about right now is this bottom left corner, because it's going to actually go through the part, and I don't want that. I just want the outside edges, so I'm going to leave that alone because it's going to be blocked out anyway. At this point, I need to draw my front and top views. So I have my front ready to go. I need my right and my top in there. So I need to add any vertical lines. They're going to stay vertical. And any horizontal lines, remember, if we look at this, it's a horizontal line. They stay horizontal. The only things that are on angles here are going to be our depth marks. So to begin with, let's draw our top view and get that set up in there. And you're really just estimating how far back you think they are. This is totally up to you, what you think looks good. There's some math you can do to figure it out properly, but I'm not concerned about us going through that. I just want to be able to find out the general idea of what it's looking at, because there's really no right or wrong as long as you're getting the basic concepts down. So I drew a horizontal line in the back, which represents my line on my front view, or on my top view, excuse me, back there. And then that point connects down, and I want to drop a vertical line from that. So I'm going to take my point and drop a vertical line down. Now at this point, all I need to do is go back in and connect my lines. 1, 2, and 3. And this is why it's important to draw those lines going to the vanishing point, because without them, you wouldn't be able to connect those points very easily, or draw the lines originally to begin with. But that's a 1-point perspective. Now you can see it's a little skewed, it's a little out of whack, it's not a perfect cube, and it's never going to look perfect. With these drawings, you're always going to have a little bit of wiggle room, which is nice because it's hard to get something wrong here. So let's take a look now at a 2-point perspective and see how that works. Again, you're always going to start with a horizontal line that's called a horizon line. Instead of 1 point this time, with a 2-point perspective, you're going to draw 2 vanishing points on your horizon. From there, you're going to draw a vertical line that represents your tallest height, and that vertical line should be a construction line to start off with. On this part, it doesn't matter that much, but on other parts, it will matter a whole bunch. From there, you're going to draw construction lines back to both of the vanishing points, and you'll complete your front, top, and right views. So let's go in here and draw it now and see what we can get. So I'm going to start off by drawing my horizon line. I will draw 2 vanishing points, one on the right, and I'll add another one on the left. And then I can go in and draw a construction line that is my tallest height, which I've done there. From that point, I'm going to take construction lines and draw them back to the vanishing points. So the top of this line is going to go back to each side, and the bottom of this line is going to go back to each side. So I have the initial points set up. This line right here, where the corner is kind of at, represents the front corner of my part. So I like to start off with my front view all the time, so that means I need to add a line over here and connect the dots. Remember, on 1 and 2 point perspectives, any vertical line will stay vertical. It's true of both of them. The only difference between 1 and 2 point now is that there's no horizontal lines to be represented inside of this. In a 1 point, there is horizontal lines. In a 2 point, there is not. So I have this. I need to drop in my vertical lines, and I'm going to do this as a visible line because that's what it is. It's a visible line. I'll drop that in there, and I'm going to darken in my front line as well. So I have the 2 lines of my views done. I just need to connect them with a line, which I can do here, and that will complete the front view for my part. Again, it's going to look a little funky. It may not look perfect. That's okay. Now we need to get our right view drawn in there, and we need to figure out how to do the top. So the front view is done. The right view is pretty easy. It's basically the same thing. I have a vertical line in the front. I need to do a vertical line in the back. Again, you can estimate where that's at. I'm going to say it's roughly there. I don't really know. But that's okay because we're just doing some estimations. And then I have lines that connect those 2 together. So I'll go in and connect those. So 1 and 2. The last piece that we need to do is figure out how to do the top view. We know what it's supposed to look like, but how do we do that on here? The process is pretty simple, but there are a few little tricks that you need to know. Our original vertical line that we drew, if there are any corners that meet on the right side of that vertical line, we need to take that corner and run it back to the vanishing point on the left. So I'm going to take the vertical line, that we have a corner there that happens to the right of my original vertical line. I'm going to bring it back to the left vanishing point. If I have any corners that happen on the left side of my vertical line, I need to bring them back to the right vanishing point. So I just have this one corner here. It's going to go back to the vanishing point on the right because it crosses over our visible line there, or our vertical line there. We don't worry about these 2 bottom corners. Even though we drew corners, we don't have to worry about them because those show the insides of an object. And if we look at our isometric here, we don't see those lines, so I'm not worried about them. And then it's just a matter of going in and darkening up the lines that are supposed to be visible. I have a line here, which represents this guy right there, and it goes back to a cross mark, which will interact with the line right there. So I'm just going to go in and connect those dots. And then I have a 2-point perspective for my cube done. Again, these are going to be a little funky. They're not going to look quite right, and that's perfectly fine. But these are how you do 1 and 2 point perspectives. Always, always, always start off with the horizon, then add in your points or your vanishing points, and then either start off with your front view or start with your tallest height. Then from that point, you take your lines or endpoints back to the vanishing points, and then you start drawing out the views that are needed. It's not a hard process, but it does take a little bit of practice, and if you have problems with it, please let me know. But that's the basic setup for what we're doing here.
Now, how is the perspective projection really happening? In a real world, the object exhibits perspective foreshortening. Distant object appears smaller. So let us see the basic situation. How is this image formed? So here I have an eye which focuses a rabbit onto the retina to form the image. The distance to the rabbit is the depth axis or the z-axis, and the distance of the rabbit is z. The eye focuses the image onto the retina, which is at a focal distance f. Now, to represent it better, let us rotate this and bring it in front and see the triangle in this way, where I have got my rabbit which was upside down is made straight, and so I have my distance, the main rabbit is at a distance z, and my screen is at a distance f. So let us redraw this image, and here you will have the z distance is to the rabbit and the screen is at an f distance. The point of the rabbit is at P of x, y, z, while the screen coordinates of the rabbit would be P prime of x prime, comma, y prime, comma, z prime. In this case, z prime will be equal to f. So let us redraw this without the image. So trigonometrically now we can solve this problem by taking different ratios. I know that the ratio of the height P versus Z is equal to the height of P prime versus F prime. These are properties of right angle triangles, and from this simple trigonometry I can say that F by Z is equal to x prime by x and y prime by y. Now this can be written as x prime is equal to f times x by z and y prime is equal to f times y by z. Now this is a transformation where we see that x is being scaled by a variable f by z and y is being scaled by a variable f by z. Now z is a variable, so if we put it as a scaling factor in the matrix, it becomes a nonlinear matrix. Can we do some process through which we would get a similar effect without making the matrix nonlinear? That is, the matrix will not have the z component as part of the matrix and still provide us with a scaling factor as given here. So here I have got z prime is equal to f times z by z, which is equal to f. So the depth axis of the eye is reduced and all the depth information is replaced to a single plane at a distance z equals to f. So I have got f by z is equal to x prime by x, y prime by y. So what could a matrix look like to do this? Now we have the relationship here, x prime is equal to f by z times x, y prime is equal to f by z by y. So, and of course z prime is equal to f. Now let us, for the sake of argument, let us take the perspective projection matrix as shown here in this figure. What you see here is that the three-dimensional matrix is an identity matrix, But what you see here in the 4 by 4 matrix, you have an 1 by f term which is coming in the omega axis. And please note here the omega dependent on omega is made 0. So having 1 by f here, the omega term becomes dependent on the variable z. So if we multiply this matrix by the x, y, z coordinate, I would get the value as x, y, z, since it's an identity matrix, and the omega term is z by f. Now, for homogeneous 3D coordinates, we need to have omega prime should be equal to 1. So what we should do is that to obtain homogeneous coordinate, we need to normalize x, y, z by z by f. So I get my new coordinates, or in the 4D, the real domain coordinates are x by z by f, y by z divided by f, and z by z divided by f. This amounts to values of x by z times f, y by z times f, and f. So though the matrix is invariant with respect to x, y, and z, by using the homogeneity condition in affine transformation and keeping omega prime is equal to 1, normalization of omega prime helps us obtain a perspective projection in a linear transformation by the affine transformation as shown above. Now, since this transformation is in a matrix format, as shown here, now that we can express perspective foreshortening as a matrix, we can compose it onto our other matrices with usual matrix multiplication. End result, a single matrix encapsulating modeling, viewing, and projection transforms. So perspective versus parallel. Perspective projections, the positive point is the size varies inversely with distance. It looks realistic. Distance and angles are not in general preserved. Parallel lines do not in general remain parallel. Parallel projection, on the other hand, good for exact measurements. That is why you use it for construction of buildings or mechanical structures. Parallel lines remain parallel. Angles are not in general preserved, less realistic looking. The perspective projection is shown here, where the image is a reduced size, is a conversion of the building to the eyes. When we converge every point to that, the screen will be approximately reduced in this same ratio. While here, in the other case, the screen will have a same size as the actual image. Of course, you may first apply a scaling function, reduce the actual building, and then do an orthographic projection. So here you have the classical projections. In the orthographic projections, I have the front elevations which are oblique, and plane oblique. I could have an isometric projection, 1-point perspective projection to 3-point perspective projection.
Before explaining how projection works, let's talk about how the perspective camera is set in THREE.JS. It's similar to the orthographic camera. In fact, the creation call has fewer parameters. We know what the last three are. The aspect ratio is the image width divided by height, followed by the near and far planes. Remember the view frustum? It's back at last. The near and far distances are measured from the tip of the pyramid, where the camera is placed, down a central axis. Back when I was a young man, we called near and far by the names hither and yon, which I think is more poetic. You'll still occasionally see the terms hither and yon used in products, so keep an eye out. The first argument for the perspective camera is the field of view. This is the angle between the top and bottom planes of the view pyramid. Notice that in THREE.JS this number is specified in degrees, unlike many other angles which use radians. The field of view along with the aspect ratio fully describe the locations of the four sides of the pyramid. For the orthographic camera, we define the location of every side of our view volume box. Here the view is assumed to be symmetric around the central axis. In other words, instead of a top and a bottom value, we need just a single angle describing both, the field of view. Same thing with the right and left. The aspect ratio along with the angle is enough. This is THREE.JS's way of doing things, and 99% of the time it's what you want. That said, it's entirely possible to specify each side of the pyramid, and WebGL itself has a frustum call that does just this. If you later change values on the camera itself, such as the field of view, near or far planes, in THREE.JS you need to call camera update projection matrix in order to have these changes take effect. For most demos, these camera parameters are usually set once on creation and rarely touched, so THREE.JS doesn't spend any time checking them each frame. If you change these values while running your program, calling update projection matrix has THREE.JS evaluate these parameters and form a new projection matrix.